All right. Well, welcome to the very last Papers We Love of the year. Whoop. Yes, this is our second year, so we're closing down the second year, and it's very nice to see some of you are new. Thank you for coming. Hopefully, we'll see you next year. And we're here to do something different. We have normally a mini talk, which is a little bit shorter, as the title says, and a full-length talk. And for December, we thought that we're going to close the year with like two mega headliners, thought leaders, visionaries of our industry. So we have Nathan and Chris, and I tend to introduce people with their bios and something fake about them as well tossed in. So here's what we came up with for Nathan's. All right. Nathan is currently working on low latency content distribution at Fastly and has previously hacked on improving the performance of language runtimes and OS supervisors. His first exposure to OS research came as a graduate student at the University of British Columbia. Also, his life is the basis of a new Netflix original series called Sugar God, and it's a show about the cutthroat business of growing maple sugar. Because he's Canadian. So let's give it a round of applause for Nathan.
Well, thank you, Inez. Oh, my goodness. All right. All right, I think I've got the right button here. Okay, hey everybody. Thanks so much for coming tonight. Before we get started, I'd like to thank certainly Inez and Elaine, who I think is out of town tonight, and the rest of the Papers We Love organizers for putting together what has become my favorite meetup in the city. So it's an honor to speak with you tonight about two views on OS scalability. Okay, so as Inez said, my name is Nathan Taylor. I've been working on low-level systems for the bulk of my career, including hypervisors, language runtimes, and right now, low-latency web content delivery. So tonight, we'll be discussing two papers. The first one was published at OSDI 08 as entitled Cori, an operating system for many cores. And the second one was published by a lot of the same authors at the same conference 2 years later, and it's entitled An Analysis of Linux Scalability to Many Cores. So both these papers approach what I'd say is one of the more fundamental questions that operating system papers have tried to tackle over the years. Namely, what are the interfaces and primitives to an operating system, or what should the interfaces and primitives be to an operating system kernel? In particular, these papers concern themselves with operating systems that are meant to run on so-called many-core architectures, which are machines with dozens of CPU cores, so very parallel server deployments. So this is a problem that the research community feels that we have to tackle because, as we'll see, both papers point out that as the number of cores in a computer increase, we observe that we spend an increasing amount of time in the kernel, even if we're running applications that don't necessarily have a lot of shared state or require a lot of inter-processor or inter-thread coordination. So this is Papers We Love, after all, so it's probably worth spending some time talking about why I chose these papers. First of all, I think the work is applicable to software developers who don't themselves work on OS kernels. It's easy to sort of rat hole yourself in reading low-level systems papers that are just about kernels, like it's always like very fun, gory stuff, but there aren't a lot of broad lessons. But I think in this work, there are a lot of broad lessons. By and large, the techniques that the authors use to solve their problems are applicable, I believe, to the general software development crowd. Next, I like the way these papers are written. They're not terribly gory papers. They read pretty well. I find that they're pretty accessible. A lot of systems papers don't have a terribly well done evaluation section. Often there's like, well, we ran one benchmark on one machine and it worked kinda, so therefore success. But these papers, I think, do actually a very good job. And I think more systems papers should follow suit. And lastly, the notion of what to do with many core architectures was something that the research community was very concerned about when these papers were written. So I think it's a good encapsulation of the systems zeitgeist around like 2008, 2010. But also, I'm presenting these two papers together. And one of the reasons why is I think it's useful to consider the work as a study in contrasts. As we'll see, they tackle the same issue of operating system scalability, but they reach very different conclusions, and I think that's an interesting thing to realize. It's also kind of a study in meta-research. I think there are lessons about the act of doing research that are very interesting when you consider the two pieces of work together. Okay, so first, let's talk about Cori. If I had to sum up the conclusion of this paper in one sentence, it would be that we need a new approach to OS scalability. They say that the semantics of current OS primitives don't serve us well because we have to maintain backwards compatibility from an era when we didn't have to worry about large multiprocessor architectures. So as an example, the authors talk about a concurrent program. All it does is it just duplicates a file descriptor. It's like completely embarrassingly parallel. It just duplicates a file descriptor and then closes it right away. They point out that the POSIX standard mandates that all file descriptors have to be visible to all threads in a running process. So this alludes to the need for a shared data structure in the kernel to keep track of all these open file descriptors. So what we would expect to see is that because every file descriptor is independent of all the others, we could see something kind of like a linear scalability graph. And every time someone shows a hypothetical linear scalability graph, because they're going to show you one more, which is not. So it's interesting to see that with 2 cores, things bottom out immediately. So this is because in a multiprocessor system, that kernel data structure will always be in the closest processor cache, which is called L1. L1 is private, so it's not shared between cores. So if it's in the cache, it's very easy to read. They cite 3 cycles to read from L1, which is pretty darn fast. But the moment we go to a second core, we have to go to a shared L3 cache, which takes 10 times, order of magnitude more time to take. And also, because it's now shared, there may be contention on this data structure. So really, at a high level, the problem is that the OS doesn't really give us a choice here. If we know for a fact that we don't have to share internal data structures between cores, we should be able to tell the OS that and then have it do the right thing. So the primitive that Cori provides in order to make this happen is what's called a share. So every executing CPU core has in its kernel address space something called the root share that any potentially shareable data structure will hang off of. So here we have one such data structure, just a file descriptor, which we opened just by calling the open system call. So this descriptor is now private by default. The reason why is because it's only associated with one core. So if we trace back up through the shares, we only get to one core. We can also create new shares by way of new system calls that the paper defines and associate them with other shares. So what we end up with is kind of a dependency tree of sorts. Now we can associate our file descriptor to that second share and then associate that share with another core's root. And now the kernel now knows through this declarative specification that the FD's data structure is no longer privately held. So that same benchmark with using shares scales the way that we would like it to, which is great. In the evaluation, they built the share mechanism on top of Linux, so that's why it says Linux shares. But the mechanism is still the same, so that's great. So a similar problem that's slightly more complicated involves keeping track of memory mappings in a concurrent program. So if you're not super familiar with concurrent programming, that's cool. Basically, there are 2 ways for a parallel or concurrent application to share memory. One way is through a shared address space. So if you program a multi-threaded program, this would be an example of one. So every thread can access all the memory of all the other threads. You shouldn't stomp on each other's thread local stacks, but there's nothing stopping you from doing that from the operating system's perspective. The other way to do it is by having a private by default address space. So if you have a program that forks children, or if you have completely separate processes that share memory through shared memory segments, this would be what this is. So I just said a lot of words very abstractly, so let's try and visualize this. So this is the first model. This is a threading model. So a problem with this approach is that each thread will need to request more memory from the operating system to grow its stacks, like so. Because there's two threads in this example contending sort of on the same conceptual data structure, which is our memory mappings, this has to be done under a lock, right? It kind of makes sense. So the other way you do it with the other approach is, if you recall, we'll have two cores with their own private address spaces, and then we just manually share what's needed. And like this makes sense, right? Like we hear a lot saying, like, it's very good to share nothing by default. There's a lot of advantages to doing it. But there's an interesting implication of this, which I think is actually kind of cute. Because there is, in the first model, there's only one page mapping. And as we discovered, Linux uses another very nice technique called lazy instantiation to map memory in your RAM to your virtual address space. And it does this only when the first time that you touch a region of memory, which is called a page. So the first time you touch a page that you never touched before, oh, sorry, I should say, and then because there's two separate address spaces over here, there's two separate page mappings. So the first time that a process touches a page, there we go, all right. It triggers what's called a soft page fault. This is where execution goes back to the operating system, which then fills out that lazy data structure and then updates the page mapping. So there's actually an advantage to sharing state here, because when, let's say that core 1 triggered that soft page fault, now when core 2 touches that same region of memory, it's already been filled in. So there's no need for a second soft page fault. But on the right-hand side, when we have a shared nothing approach, we trigger 2 soft pages faults, or n soft page faults per page modification per thread. So really, the problem is an impedance mismatch. We have to choose between either locking a single memory space data structure or suffer additional traps into the kernel to redundantly initialize redundant copies of the redundant memory space data structure. So the second abstraction they provide is very similar to a share. They call it an address range. One of the things that wasn't clear to me about this paper is why they split up the two primitives, because to me they are very similar. So each core starts out with its own root address range that is private. And through the same mechanism as with shares, you can share a region of memory by having R2 depend on 2 roots and have a shared memory segment added as a dependency to that address range. So in their workloads, because remember this paper was written in 2008, so MapReduce, the cool new hotness. The private, one of the examples they use is for a MapReduce framework. So the private memory regions are for the mappers, and the shared address space would be for the reduce operation. Another thing that they do that's kind of cool is they have 2 cores, and they pin different parts of an HTTP request on different cores. So you have a private TCP/IP stack that handles the networking layer, and then a separate core that handles the HTTP, like the application layer protocol. And they communicate over a shared memory segment in order to pass data between each other. So what we have here is the relative performance of Cori on these workloads, or I guess this is over MapReduce, over Linux. They say that in the paper that Cori doesn't perform super well for less than 8 cores because Cori's soft page handler is not like production caliber the way that Linux's is. So this is a typical way you punt on these sort of things. You say like, well, if the Cori codebase got as much love as Linux did, then it would perform even better. But for 16 cores, they had a 16-core machine in 2008, and this is what they ran. They got 25% improvement, not too bad. One thing that I do like is that they tie their experimental results back to their hypothesis. So what they do here is they have per core shares versus a global share. I think this is this is the file descriptor microbenchmark. And they say, well, you have linear scalability with per core shares, and the number of cache misses correlates with the performance improvement, which I thought was a kind of nice way of tying it back to their hypothesis. So before we talk about the second paper, I want to bring up a question. This is a very broad question. In the most abstract sense, what is research? So, I mean, we could talk about this all night. A friend of mine, Stephen Kell, who's a postdoc at Cambridge, has a definition of systems research that I came across a couple of years ago, and I really like it. He says that it is the practical consequences of an idea. We can talk, you may have a definition you like more, and I might encounter one that I like more down the road. But this is a definition that I've gone back to over the years, time and time again. So in Cori, the idea is that applications should control sharing, right? They say exactly that right in the abstract. And the consequence of that idea is that we see far better scalability for parallel workloads as a result. But what if the idea was that applications shouldn't need to control sharing, and any and all scalability fixes should happen behind the kernel abstraction boundary? Well, this brings us to the follow-up paper, an analysis of Linux scalability to many cores. Indeed, if you look back at what the abstract says for the new paper, the abstract doesn't start with an assertion about whether we should or shouldn't control sharing. My notes say scaling, that doesn't make any sense. The abstract only says that we studied a suite of applications, and the conclusion that we reach is that there's no fundamental problem with the current state of affairs. In a word, instead of creating new primitives, let's just fix the existing ones. So this was 2 years later. This was in 2010. So the authors are able to get themselves a 48-core machine. So this is great. This is even more many core than many core from 2008. And they start by observing that their suite of applications all spend a lot of time in the kernel. So if we want to be studying kernel scalability, that seems to make sense. And a lot of them scale very badly under stock Linux. So in particular, Apache does a very, very poor job. Métis is a MapReduce library. And then psearchy is a file indexer. But I think everything else is a pretty well-known open source. Yes, Jeff Hodges, do you have a question?
I'm just wondering which Apache, was it NPM, or like did they say which kind of Apache?
They may have. I don't remember. Yes.
Is make doing so well just because everybody has been always calls make with a J flag?
The question is, why does make perform well?
Is this like a problem that they've been doing forever? Or?
That's a good question. I would guess because make is probably a lot of short-lived parallel processes. You spin up. You're compiling an object file, so you kick off the compiler, and then you can kick off the linker. The nature of parallel is it's more of an embarrassingly parallel operation, whereas stuff like the MapReduce library or Apache is like a long-lived running process. But they don't discuss it in the paper, and that is just a guess of mine. Okay. Oh my goodness. No, I don't want to give that talk.
Why are there so many slides? I didn't make that many.
Okay, cool. They're all good, thank goodness. All right. So the authors trying to tackle these performance bottlenecks by doing kind of the obvious thing. They benchmark the result. They identify basically what is a point fix, like a single bottleneck in the application, and they say, okay, well, does it scale now? If it does, fantastic. If it doesn't, they either try again or they conclude that it's an intrinsic problem that they can't improve on. So it's either a serial code path, so Amdahl's law tells us that there's only so much we can do there, or that it's a hardware scalability issue and there's nothing for them to fix in software. So the paper lists a whole bunch of fixes, most of which didn't require application changes, which I think is significant. Most of the changes happen in the kernel. And they fall into a few different categories, which I color-coded here. So I'm going to talk about a couple of these classes of problems. Oh, sorry. Yes.
Does the application name there, does that just mean the applications which surface the problem?
Right. Sorry about that. So on the left, we have sort of the class of problem. The bottom half of the line, it's the solution, and on the right, it is the programs in the benchmark that exhibited this problem. So, for instance, like only Apache had a problem with the accept file, the accept socket. Exim had false sharing, that sort of thing. Cool. Thank you. All right. So first of all, let's talk about changes to improve performance that came about because of bottlenecks with the machine's memory coherency protocol, particularly with using locks. So here's a piece of kernel code that protects a hash table with a lock. So far, so good. Nothing too weird. Now keep in mind that if your hash table is already in your cache, like if you think about what a hash table does when it's looking something up, it's doing very little. I would guess that this is a very fast operation, maybe just a few dozen CPU instructions. So it should be very fast. So a scalability problem can manifest, excuse me, when the lock that protects that hash table is in a remote processor's cache. So if you saw my mini talk a couple months ago, I spread the good word that your computer is actually a distributed system. And reading memory is very much a reading remote memory sort of operation. So different cores in your computer are connected over an interconnect fabric. So this is your computer's bus. And it's really like a network. And each hop adds latency of several hundred cycles per hop. I think in the paper they say between 1 and 400 cycles. 4 seemed a little high for me, so I said 1 to 2 just to be safe. But the point is that lock is more of a scalability bottleneck than actually what the lock is protecting. Also, for locks that are highly contended, so when you have a whole bunch of cores trying to get access to the same lock, you'll have all the CPUs frantically trying to read the state of the lock to determine whether the state of the memory has changed and whether they've got the lock. So what this forces is a whole bunch of basically remote procedure calls from core to core saying, can I read this? Can I read this? Conversely, when the lock is finally unlocked, it has to broadcast a notification that the state of the memory has changed to all the cores that are basically waiting for a notification. So any core that has what we refer to as a shared cache line. So anything that's like been recently accessed has to be broadcast to. So they offer 2 solutions for this. The first solution is pretty straightforward. They just have a per core data structure that's read as a cache and gets invalidated when the cache is written, when the hash table is written to. They're able to do this because they make the observation that the hash table is read way more frequently than written. They also offer a more interesting solution, which I will briefly sketch here. The authors, so in a perfect world, if you have a data structure protected by a lock, what you want to do is you want to move to what's called a lock-free programming model, where you don't have to take a lock, but you take advantage of hardware concurrency primitives to synchronize operations. And it's great when you can pull this off, but a lot of the time you can't. And here, oh, yes?
Sorry, but if we're doing mostly reads, then why don't we just put like an RCU lock on it?
The question is, why don't we use a particular kind of lock?
I mean, they use a spin lock.
Right. So at the time, they were using a ticket lock. So this is from the version of the kernel that they were using, which is 2.632. More recent versions, I'm pretty sure, actually do use an RCU lock. I'm going to punt and say that there's an inherent scalability bottleneck with lock-based synchronization. That, yeah, Devin, I said that for you. And then even if you use a fancier lock, you will still have sort of an inherent queuing effect. So a fancier lock will help to some extent, but often a way to achieve like very good performance is through lockless parallel programming. Yes, and we're going to talk about that in about 10 slides. So what they do is they say, well, we can't make the algorithm completely lockless, which is a bummer. But they do point out that in a lot of cases, if you are just reading the data structure or updating certain fields within the data structure, you are actually able to use a lock-free algorithm. And they describe a way that's actually used elsewhere in the Linux kernel to do a lock-based approach, determine whether a lock is being held for like a more global operation, and then fall back to a lockless approach, fall back to a locked approach if they can't at this moment do lock-free programming. This is intended to be like a very brief sketch of how they do it. They describe it in the paper in a relatively detailed way. And as I said, Linux also uses it for the page cache. So if you want to go read the source, Yeah, the page cache uses a similar approach. So that's cool. So I just answered a question by saying atomic lock-free operations are exactly the thing you always want. But here's an interesting thing. They did this fix and then iterated back to see where a performance bottleneck was. And they noticed that as a whole, the system got slower. Not necessarily in any one function, except for this one. But operations that had nothing to do with the lock that they fixed ended up taking more time. And this function called dput started appearing in profiling results. So why would you start to see scalability bottlenecks because of these single atomic instructions? So the authors posit that over-relying on atomic instructions, which are expensive because they require hardware-based locking, can actually slow down unrelated operations because the interconnect is being saturated by lock-unlock operations so that other memory transfers get stalled. So they proposed this. They proposed something called a sloppy counter as a replacement for atomic counter operations. And let me walk through kind of what this looks like. So imagine that we have 2 cores. So a sloppy counter is a data structure with a shared counter value. So far this just looks like if you had to implement an atomic counter, you would just have like one counter, like an int. But you would also have additional private counters, each on their own cache line, so there will be no contention for each core that's going to be operating on this sloppy counter. So we can increment a sloppy counter by bumping the shared atomic counter at the expense of bus contention, as I said. But we can decrement a sloppy counter by subtracting the value in our private counter. So notice that right now, the value of this counter is 0 because all the counters sum to 0. Now, if core 1 wants to bump the ref count again, it can do so straight from its own private counter, avoiding having to synchronize on the shared counter. So notice that we have a count of 1, and the sum is now all 1. And we fall back to the shared counter when we have no values in our private counter to use up. And of course, the other core can be accessing the shared data structure together. And eventually, when the count would be 0, our data structure, based on what it's counting, might look something like this. So periodically, we can go ahead and manually rebalance the shared counter if we want, so that everything is just reset to 0. So here's, this is a little bit hard to read. So this is the result of using the per core lookup and sloppy counters. So the gray one is the stock Linux benchmark. And it's interesting to note that there's a weird kink right at number of cores equals 40. So if you had a 32-core machine, you would only have, sort of the first 2/3 of the graph, and you would say like, oh, well, from our perspective, this should scale perfectly fine. There's no reason why we would have, any problem because, we basically have linear scaling. And it's not until we hit a sufficient number of cores where we realized, oh, shoot, actually, things start plummeting after a certain point. So we continue to scale by adding the per core lookup, and we got a little extra boost from the sloppy counter. So we see good performance without needing any new operating system abstractions. At least at 64 cores, that's true. Really, the point of this paper is that it's not saying that Linux as a architecture or the primitives that Linux provides will always be good enough. But they're saying at this point in time, with 64 cores, we don't need anything better. Shared memory is a comfortable abstraction. And as long as we can maintain it without burdening applications by having a new programming model, it's a worthy goal to try and achieve at least. So the Linux scalability paper talks about scalable implementations. If you think about papers as being like film series, the final paper in the trilogy, the scalable commutativity rule, which was published at SOSP 13, focuses on the scalability of interfaces, where there's no possible scaling implementation because of, say, for instance, existing POSIX compliance. So maybe the way to close up the presentation is by telling you all about a mistake that I made. So these papers, as I said, were published in 2008 and 2010. And in 2009, I started grad school. I wasn't expecting that to be a laugh. Jury's still out. And in fact, the first systems conference that I attended was OSDI 2010, where the Scalability of Linux paper was presented. So I was in the audience as this paper is being presented. So you can imagine that, like, as a junior grad student, I'm super excited about Cori. It's like, yeah, we got to throw away this existing operating system primitives. Like, we need like cool multi-kernel, unikernel, Haskell, whatever thing. Like, yeah, we got to come up with research that's going to totally blow away the old world. Shiny new things are great, right? Well, the way that I interpreted the scalability of Linux paper was that it was a refutation or a retraction of the Cori paper. I remember leaving the presentation saying, well, what's the point? Like, they've gone back on their old work, low-level systems work is solved, and Linux is good enough. And this actually really affected the rest of my grad school career. It wasn't until years later that I realized the fact that this isn't the case. The papers don't contradict each other. You can publish opposing solutions to the same problem, and your contribution is like the sum of those papers. It's not a zero-sum thing. So your work can coexist as part of a larger body of work, even if you don't always come to the same conclusion. So this is about all I have to say about these papers. I thought I would put up a few conversation starters, so for when we go to the pub, we have something to argue about. One of the things that the Cori paper doesn't really talk about is how you hand shares from process to process. They have a magic UID that they send over sockets. So there's plenty of work to think about around access control lists. How do you make sure that you don't just choose a bunch of UIDs and suddenly have a whole bunch of access to things that you're not supposed to have? And if you are a programming language person, it might be interesting to think about what kind of language support might nicely fit into shares and address ranges. Next, cloud hosting was around in 2008. I had to look this up. AWS started in 2006. But containerization, well, if there's anyone from Sun here, they'll tell me, well, Sun OS 5 had it back in the 80s. But it really wasn't like a big thing like it is now. So a question to ask is, how could modern OSs be virtualized over a subset of a many-core machine to scale well, but with an extra layer between it, either being a virtual machine monitor or a host OS for containers to run on top of. And lastly, I like this question. This was asked at the OSDI 2010 presentation. From the perspective of positioning your work, could the authors have published the papers in reverse? They didn't have an answer, but maybe we can come up with one tonight. So that's about all I have. If you have questions, I would be very happy to answer them.
Ooh, okay. So I have macaroons.
Oh, my goodness.
Okay.
I don't have a question, but I have a brief comment.
Oh, good. I love these.
Yeah. So I've never heard of either of these papers, actually. And when you got to the second one, which is the analysis, well, I should first apologize that I didn't read them before, but I was preparing my presentation. Yeah. And so the analysis of a Linux scalability to many cores, when you showed the sloppy counter, I was like, well, that's like a CRDT counter, isn't it? And then I was like, well, man, shouldn't he have cited that in their paper, right? Because their paper is they have one that predates and postdates the 2010 paper, right? Mm-hmm. But then you showed the scalable commutativity rule, right? And so that paper directly complements the CRDT work, right? Yep. And Neha Narula's later research and her presentation on this paper, I believe it was at Papers We Love in New York, was look at that face is very similar. So I think it's really interesting to see that kind of idea is like concurrently being developed in like two different communities, and like I think it's a testament to the statement you made about single machines with multi-cores being distributed systems, right? Like it really backs that claim up, right? So
I would love to see more overlap between those two spaces.
Yeah, I agree.
And I think if we believe that the number of cores is going to go super huge, like if we have thousands and thousands of cores in a machine, having the same kind of cache coherence protocol where everything just sort of happens under the hood and you shouldn't have to think about it too much may not be possible any longer. So the programming models between a distributed system and a very large shared memory multiprocessor machine may not end up being that different. So the sooner we can get on the same page about these things, I think the less pain we're all going to have.
You should come do coherency protocol and divergence in my research group.
Oh, well, geez, that was This is like when you go to a conference and you give a talk and then people come up to you and ask questions, but really they're just selling their, their startup to you.
It's the job offers, right? It's the job offers.
So Nathan, great talk.
Thank you.
You educated me. I had not read the first paper. I had read the second paper. and I
Chris,
was
Chris, do you hear that?
I was as
Yeah.
fooled by the second paper as you appear to have been by the first paper. But then there was another paper, I think, that was published much more recently, I think, and I was trying to look it up right now. It's by the guys in Zurich at ETH, which essentially completely corroborates the second paper, that there are serious, scalability limits. The first paper, and there are serious scalability limits, and it's not about the language, it's not about Linux, it's actually about the computer architecture you're running on. And they showed that, for example, there's no point in buying a dual socket Intel machine because the second socket doesn't give you any advantage at all. And so the interesting question is, are we focusing too much on this, what you said a moment ago, on this shared memory abstraction? Is it something we've fallen in love with and that we're comfortable with? But really, we need more than one abstraction. We need perhaps a communication abstraction, and we need a computing abstraction, and both are necessary for a complete world.
Mm-hmm. That's a very interesting question. I feel like a lot of the design that we see in commercially available many core systems stems from the issue of backwards compatibility. So you could imagine if you are a hardware designer, and I know there's at least one in the audience. Hello. Could have like many interesting opinions about how hardware should be designed to scale to thousands of cores. But the fact is that if I can't run my existing shared memory software on top of it, then from the marketing perspective, it's a hard sell. It would be very interesting to see if we had a clean slate what we could come up with. And that's one of the reasons why I like sort of the blue sky architecture papers like the Corey paper, because it said if we throw out the existing world and we're willing to make either changes to application code or say, well, we're entering a brave new world, what can shake out? But I have very little intuition about what the right answer to your question is.
You kind of poo-pooed, maybe this was like your 2008 or 2009 self-talking, but you kind of poo-pooed like the unikernels and that Haskell stuff. I mean, I really like what Mirage is doing, and in these papers, why do we want that? Like, one, why do we want this shared mutable state? And two, the papers themselves show an example of a HTTP server. Why can't we just boot up a unikernel for this request and then it goes away when it's done? And is that something that that's not a relevant thing, or do you consider that blue sky thing?
So for clarity, in case there was confusion, I think unikernel stuff is great. I think it's actually the abstraction we want. Briefly, unikernel is like an application level library OS that runs on top of hypervisor. And I really like that work because so much of what we do is adding layers of abstraction between things, and unikernels remove layers between the hardware and the application. So I think like unikernels are great. I would argue it's not the right approach in this case because they're talking about, unikernels are really a different beast than operating system stuff.
Well, you spin up a new one for each core.
You spin up a new what?
For each request that comes, for any kind of thing that you need, you just delegate it to a core that's not doing much.
My guess would be, and it's super dependent on workload. I think at the lowest level, spinning up the overhead of spinning up a unikernel is probably you need something in the middle there. Yeah.
Oh, hi. So I had a question.
Yes, hi.
So you kind of touched on the relationship between sharing and access control and mentioned access control lists. And I was curious if you have seen some of the papers around object capabilities, like Mark Miller's thesis, Robust Composition, which talks specifically about the relationship between concurrency and access control, and how object capabilities or capabilities in general can provide a sort of unifying concept between the two of them.
I haven't, but that sounds very interesting. Who is the author again?
Mark Miller, and I
Oh, it was Mark
think
Miller.
I will
yeah.
be giving a talk about that next year.
Okay, brilliant. Well, I look forward to
Here.
it. I don't know. The
Cool. All right.
All right, we have time for one more question, and then after that we can make a little break, and then we start the second one. Okay, Gil, get the last one.
Oh boy. So I hope this isn't too much of a trolling sort of question.
excellent, good.
Why do we need to run OSs on 48 cores? So I think that's, all right. If you want to take an extreme example, if you really want to like go out to the end,
Yeah.
let's see if we can get Linux running on my GPU. Right? I mean, that's probably not going to happen, nor does it seem like anyone has any real desire to make that happen.
So this is sort of similar to like the unikernel argument. It's like this is, like it's really time to throw everything out. I feel like in a perfect world that's great, but unfortunately we have like ostensibly like 50 years of legacy code in one form or another. I think it's given that when Windows NT was supposed to be like the operating system for the 90s, right? But because we had so much stuff running in the Unix world, it never really necessarily took off. So if given that, to go to even more extreme, to go to even more of an extreme position, even if it's the fundamentally correct one, I think it's tough. One of the reasons why I like the 08 work and even stuff like the extra-kernel work, which is very similar to like the library OS stuff, is that it shows a path forward that's incremental rather than like this revolutionary change. But you're right, to answer your question, yes. What?
All right. So, hello, Chris. I'm going to introduce Chris to you. So Christopher Meiklejohn is a senior software engineer with Machine Zone Inc., working on distributed systems. Previously, Christopher worked at Basho Technologies Inc. on the distributed key value store REAC. This is from your bio, though. Inc. This is what you put in your bio. So in his spare time, Christopher develops a programming language for distributed computation called LASP. Wait. 1 second. My phone just thingy. Okay, so he works on LASP, and his scarf collection has gotten him recognized by Vogue Magazine, Inc., Mary Claire, and W. Chris is starting his PhD studies at the University of whatever, in Belgium, 2016, and he will tell you the correct pronunciation of your university. So let's give it up for Chris. Oh. This is his third Papers We Love around the world, so this is a hat trick. So you've spoken at Boston, Paris, and now San Francisco, right?
That's correct.
Cool.
I am the first. Yeah. I don't know if that's like a good thing or a bad thing. Oh my goodness, I went ahead and I'm ruining all of the fun, and that's terrible. So my name is Christopher Meiklejohn. I will start this off by saying that I get so nervous before talks, it's ridiculous. So bear with me for at least the first 4 slides, and then things will get better. So I'm going to talk about a brief history of chain replication. So I actually don't do a lot of work on chain replication at all. It's a topic that I just find interesting. So I spent a bunch of time trying to come up with a conference talk, and I was like, well, I'll kind of talk about this. So part of this talk is going to be about 8 or 9 papers. I forget the total amount. So we're not going to dig really in depth into the details. What I want to try to do is tell a story about chain replication and kind of the invention of it and where the research went, and kind of look at the various research groups that have kind of worked on it and tried to productionize it and things like that. And there's this kind of great, it's always great in comedy to have this kind of reoccurring character that comes back at the end of the joke, right? To like get that punchline. So for the purposes of this talk, that will be Robert Van Renessa. So I apologize to you, sir, in advance. So let's get right to it. Okay, so this thing is like acting like it's not working. Okay, I have to use the computer. How quaint. Okay. All right, so chain replication, right? So I like to start my talks the way I start my day, and that's using Twitter. I made this tweet the other day, and it said, observations made while writing my talk, this talk. And I said, chain replication in theory and practice mainly focuses on the difficulties of implementing proper failure detection to ensure safety. And this is one of the papers we're going to talk about today by a colleague and a great friend of mine, Scott Fritchie. And then I respond back, and then I respond to that, and I say, Hyperdex, a distributed searchable key value store, leaves out most of the information on failure detection and assumptions regarding faults. And then, in true troll, traditional troll goon responds and says, can you point to the equivalent documentation for React? And so, this went on for a while, and I eventually responded, and Jordan West, who's not here, got involved, and things got really heated, and Goon is just like a super troll. I mean, look at that Twitter handle. It's Leet Haxor, so that says something. And finally, I just said, well, React was never at SIGCOMM 2011 or whatever it was, so if we were, we would have written really great documentation. So then there were these other thought leaders talking. Some of these people are in the room today. And so Neha Narula says, well, primary backup is kind of odd because it requires a probably Paxos replicated view server. To which Peter Alvaro responds, so does chain replication, no? And then we have the response, yeah, well, chain replication is super odd, capitals super. So that's serious. And then we see that Peter Alvaro favorited it. So you'll notice a trend to these tweets is that UC Berkeley people like to favorite tweets. And so finally, another person who's in the audience today says, does any system in the real world use chain replication? Notice this is almost 1 year to the day. It seems like an academic strategy that only works in fail-stop failure modes. And then Kyle Kingsbury responds, I think the Hyperdex folks were big into it. I still can't figure out why. And then you'll notice we got the, star of approval on that tweet from Peter Bayless, so it must mean something real. So my idea is that famous computer scientists agree chain replication is confusing. So hopefully, this talk will make that a little bit better. And I almost forgot one, Neil Conway, who said he was on the I would like to come to this meetup list, but it doesn't appear that he actually came. He said, chain replication, strange that it is so well known academics, and yet seemingly so obscure to practitioners. And we see that Diego, who's here tonight, favorited that, and so did Katie, and Sean Cribbs probably would have been here if he didn't live in wherever he lives now. So anyway, what's the overview of this talk? So I'm going to walk through a bunch of papers on chain replication today. We are going to start with the first paper by Robert Van Renesse and Fred Schneider, so kind of the Cornell dream team you got going on here, published originally at OSDI 2004. We're going to move towards people who iterated on the design to try to bring this into practice. So Object Storage on Crack by Terrace and Friedman at Usenix 2009. The Fast Array of Wimpy Nodes from Anderson et al. At SOSP 2009. Chain Replication in Theory and Practice, published at the Erlang Workshop event at ICFP 2010 by my former colleague at Basho, Scott Fritchie. We'll briefly talk about the Hyperdex system in question from those tweets earlier, and this was at SIGCOMM 2011. Then we'll briefly mention the work on chain reaction, which is a causal plus consistent data store, which was done by colleagues in my research group, Sergio Almeida and Joao Leitão, at Eurosys 2013, and this was previously at the Lattice workshop of 2012, I think. And then finally, the paper, so I want to talk about Habari, but not Habari, Machi, but there's not a published paper yet, so I'm waiting, and I'll extend this talk when that content's available, but we're going to wrap it all up with paper number 7, which is leveraging sharding in the design of scalable replication protocols. And so this is a pretty recent paper at the Symposium on Cloud Computing from 2013. And as you can see, we'll bring it back with Robert Van Renesse coming in strong. So what are the themes of this talk? So the thread that I want to draw through kind of all of these different papers and get you thinking about and thinking about how you do this in the systems that you build today is kind of two components. The first is the idea of failure detection, right? So how do we actually detect that a system on an asynchronous kind of unreliable network, how do we know when a system has failed? And we know that there's been a lot of canonical research on this topic, basically kind of culminating in the FLP 85 result based on consensus that shows that this is effectively impossible without the use of timeouts. And finally, I want to talk about the notion of a centralized configuration management service. And when I say this, I mean a single server or I mean something like view stamp replication or Paxos or any of these techniques where we have some linear order over some highly available thing and fault tolerant thing that appears to be a single machine, right, in the network. So these are going to be the kind of two reoccurring themes in this talk. So we'll dig right in. We'll start with the kind of canonical paper on the topic, chain replication for high throughput and availability. So to kind of set the stage for this talk, we're not going to talk about relational databases. We're going to talk about a storage service, an object storage service, that has two function calls. The first function call is going to be a read operation that takes an object ID that returns some object, which we're calling V here. And then the second operation is the write operation, which takes an object ID and some V and writes this to the system and then returns OK, that this object has been written to the object storage system. So kind of at the time that this paper is written, they critique two strategies. The first strategy they critique is what's referred to as primary backup. So if we go back to Neha's tweet from my beginning troll intro to calm my nerves, that is what the PB stands for. So in primary backup replication, we have a primary node that's designated leader that sequences all reads and write operations that come into it. It will forward these, so we'll have these serviced by a non-faulty replica in the system, and we'll wait till those have been written to the backup, and then we'll return to the user. And so this is going to be bounded on the max latency, basically. Your request is going to take as long as the slowest node basically takes to respond in this. And this will be synchronous. And you can do asynchronous versions of this, but we're going to specifically focus on synchronous here, mainly because we're talking about linearizability at this point. And so the other component that's required is a centralized configuration manager. Because you need something that's going to modify the primary and some number of backups. It's going to monitor these. It's going to heartbeat them or use some other failure detection mechanism to know when the backup node should become the primary node. So how do we detect the failure, and how do we respond to the failure by promoting a backup into the position of the primary? So the second approach they kind of compare and contrast to here is quorum intersection. So this is probably more familiar to practitioners who have been working with databases such as REAC or Cassandra or Voldemort or things like that. And in quorum intersection, you have read and write quorums across a series of replicas, and you ensure that these quorums overlap. So if these quorums always overlap for read and write operations, you have a guarantee under steady state without sloppy quorums that you will read the result of your last write operation. So if I write against nodes 1, 2, and 3, and I succeed, and then I happen to read from an overlapping set of replicas, maybe 2, 3, and 4, I guarantee that I have some overlapping node, and that allows me to get the most recent update. And they say, well, yeah, obviously, the increased performance here is that you want your quorums to not be all of the nodes in the system. You want it to be some subset of the nodes in the system. And then you want to kind of assemble these quorums a particular way to allow you to have this replication, this high availability, this fault tolerance property. So again, we get, centralized configuration manager, right? We got to figure out who has the quorums. What are the quorums? How are the quorums established? How do we deal with machines that go away and never come back, right? So we need to have the quorums established ahead of time. And so this is what the centralized configuration manager does for the purposes of this. So what are the contributions of the original chain replication paper? So the first is that they posit that the system is higher throughput because we assemble kind of a chain of nodes, and we'll see what that looks like visually in a second, but it's, a chain is just a totally ordered set if we think about it from a mathematical point of view. And what we want to do is not send all of our operations to the primary. We want to split the responsibilities. Like if we think of the primary backup mode, we want to split the responsibilities between multiple nodes of the system to achieve higher throughput, right? If each machine has to do a little bit less, then we can do a bit more, right? And they also want the system to be more higher available. So in terms of a quorum intersection system, typically you need to have 2 f+1 nodes to tolerate f failures. And in the chain replication algorithm that they propose, objects are tolerant to f failures when you only have f+1 nodes in the system. Finally, they want to provide a system that is linearizable. So, and that's just a total order of reads and writes. So we'd imagine this appears to be a single machine, right? Something you'd get from like a state machine replication with Paxos or similar. All right, so this is what a chain looks like. I love this slide because it's like, it reminds me of that Monty Python episode with the larch, remember? Because it's kind of like figure 2, the chain. But, and here we have the chain, and our updates come into the head node, And they are not acknowledged to the user until they're written to the tail, right? So we have this, and we have one node, and we send it here, and we send it here. And when it gets to the tail, we send the response back to the user. We send an acknowledgement. And that's an interesting thing because they say, well, once the tail has it, we can just acknowledge the user. But actually, in practice, as we see with some of these systems, it's more efficient to send acknowledgements back and respond from the head because you've already established a TCP connection. And it's really expensive to establish a response TCP connection from the tail. So that's an interesting kind of observation that you see come up a few years later. And so what we do is that if we want some object to be stable and have this fault tolerant, we need to wait till we write to all the replicas. So all of our read operations come in, and we effectively serialize all the operations on the tail. We don't acknowledge a write until the tail has processed it, and we process all of our reads at the tail. So we've effectively divided the responsibility of the primary backup system into 2 nodes. And you'll notice here, there's an interesting observation you can make that there's no acknowledgements between any of the nodes, right? So in the original formulation in the paper, we just send these writes, and we don't acknowledge anything except acknowledging the user when we write to the tail. So how does this kind of work if we want to look at it as from the algorithmic point of view? The head applies an update, so the head will take some mutation from the user, apply some update, generate some new state, and that state will basically be propagated down the chain and stored at each node. The tail is going to acknowledge the request to the user, and yeah, I mean, that's pretty straightforward. And finally, they define this property called the update propagation invariant, which says that every node, every subsequent node in the chain will have less items in its history, right? Because as the system is running, nodes that appear earlier in the chain will have more objects in their history, and objects later in the chain will have fewer objects in its history. And those objects are pending, they're in progress, they're being delivered, right? And they're not acknowledged to the user until they're written to the tail. So again, we see that if with that update propagation invariant, we'll have each node in the chain as the system is processing things, as we're pipelining writes through the system, each object will have more state in its history compared to the next object. So you might say, well, oh man, we don't have any acknowledgements, we don't have any of this stuff. So like, what does that mean about failures? How do we deal with failures, right? If a node takes some write and maybe applies it, maybe doesn't apply it, what happens? So, in terms of failure detection for the system, the chain replication algorithm relies on the centralized configuration manager responsible for heartbeating the nodes, watching the nodes, and knowing when to reconfigure the chains when a node is unavailable in one of those chains. And they got this little caveat, right, which is kind of like, goes back to the tweets from the beginning of the talk. It says, well, we assume the fail-stop failure model. Okay, well, what's fail-stop? Well, fail-stop is that processes fail by halting, and they don't perform any erroneous state transitions. So if some object is like partially being written to the disk, and maybe some of that gets persisted, well, that's what we define as an erroneous state transition. We also assume that processes can be reliably detected. So any of you practitioners in the room who maybe work for companies that have, I don't know, a few hundred servers, probably know that this is a thing that you can't really do effectively. So let's just, we'll roll with that. Cool, yeah, that sounds dope. Let's do it. So what does this mean? So if we're going to reconfigure, we have to consider 3 cases. So the first case is pretty easy, right? It says, well, if the head node fails, so they make this other nice formalism in the paper that says that a message has been delivered to some node and some subsequent node fails, then we can consider that a pending operation that will never be delivered, and they have this state transition that effectively moves it to nothing. So they say, well, if the head node dies, so some head node dies, we'll replace it with the successor, and as long as the update invariant, the update propagation invariant holds, we're fine. Now, easily follows from the update propagation invariant that if the tail node fails, we can just easily use the predecessor to the failed tail, and that can become the new tail, right? So these are the trivial cases. So in one case, you can lose an update that's only been applied to the head of a node that drops, and in the other case, and remember, like you might say, well, that sounds crazy. Remember, fail stop, yep, sure, we know when things fail, and we know that they don't perform erroneous state transitions. So yes, this follows naturally from that. And finally, with the tail, it says, well, we always know that the rest of the nodes after, the successors, will, for some node, will have lesser state. So if that node drops down, if the tail disappears, the node that is the predecessor can easily become the tail because we know it's applied all of the state transitions correctly and everything's fine. So it gets a little bit more complicated when we say, well, I mean, something in the middle might fail too, right? I mean, if we could build these systems where only the ends and the head ever failed, man, that would be an amazing world that I would want to live in. So we say, well, if the middle nodes fail, what can we do? So this can't be solved without adding acknowledgements into the system. And so it's really easy to define this. We say that, okay, we're going to have an in-process request invariant. And what the in-process request invariant states is that a history of a given node is always going to be the in-flight updates to its successor node plus the successor node state. And if we can insert that this invariant always holds, then we can easily repair chains by reshipping messages that are deemed pending. So, little diagram just to show you how this might work. Yeah, well, we say, 1 is sending results to 2, and 2 is sending to 3. 3 disappears. The configuration management service determines that 4 is still alive, so we reconfigure this way into the 1, 2, 4 chain. And then what we do is we reship the state to 4 that 2 had gotten acknowledgements from 3, because those acknowledgements flow back from the tail. They don't flow in between. They always flow back from the tail. So we just apply those updates, and then the system is fine. It's great. Seems great. And that is still not working, so I need to stop doing it. All right, so that's kind of the basic chain replication algorithm, right? It's very simple. If we have this perfect world kind of failure model, we know we can always reliably detect failures. It's really simple, right? We just kind of remove nodes that are failing, and we just ensure that the nodes that are neighboring have the same state, and everything's great, right? And we can continue to make progress. So the next 3 papers we're going to talk about are research that came within the next, I think, 3 or 4 years, that kind of challenge some of these assumptions. So they try to figure out, well, how can we make it more efficient? And how can we make it a little bit more reliable? And how can we actually use this in production? So these are research papers that try to make the system more efficient. So the first one we're going to talk about is from Usenix 2009. Usenix actually is really amazing because they record their talks. So you actually can go watch the original author on YouTube give this talk. Yeah, shout out to Usenix, right? Like, that's dope. So you should go check this out. It's in 3 parts. It's 27 minutes, and the author talks about, he mentions all of the really trendy things from 2009. So shout out to Nathan Taylor for bringing up MapReduce, because that's in this talk. And there's a bunch of really other great things in this talk, like MySQL, and things like that, right? Like things from the past. So anyway, moving on. So CRAC. So what does CRAC stand for? So CRAC stands for Chain Replication with Apportioned Queries. Right? So academics love their puns, and this is a great one, I guess, maybe. I don't know. But what's the main motivation of this paper, outside of all of these kind of incremental improvements that they propose, the main motivation of this paper is that they do not like the fact that read operations have to be only serviced by the tail, right? Because it really hinders the scalability of the system. So they want to kind of challenge this and figure out a way to do this better. They do a bunch of other stuff too, but this, I think, is the main takeaway from this paper. So what does the CRAC paper provide as contributions? So the first one is that they have it so that any node can service read operations. And this alleviates hotspots on reads, right? So we don't always have to serialize on the tail, right? Second, they kind of say, well, network partitions are real, which is great, because that's 2009, so shout out to those people for being forward-thinking, but not really, but partitioning, they say, well, during network partitions, we can still service reads, and we can service reads by any node as long as they're eventually consistent. And so they kind of, they're in the glory heydays of the Amazon Dynamo system, so they get to use this as a contribution. And finally, the final contribution of the paper is that they provide a strategy for multi-data center load balancing. So I am extremely naive of this strategy as somebody who worked at Basho for 2 years on multi-data center REAC. I'm extremely kind of critical of some of these things, but maybe they will work. I don't know. And the evaluation is kind of hit or miss, right? Because it's like 2009, and some of these systems aren't really evaluated the way you would actually run them in production. So. Now that we've brought eventual consistency, all of our favorite pairs of words together into the conversation, we'll talk about what consistency models the CRAC system provides. So again, similar to chain replication, it provides per-key linearizability. So we like that, right? And makes it very easy to write computer programs. It provides eventual consistency. So it says that if I have a write that hasn't been persisted to all the nodes, I can allow a dirty read. So they classify replicas into clean replicas, which have replicas that have a stable value, and then any replica that has a dirty value, so an in-progress value, and a stabilized value, they consider that a dirty node. So this is a node that services a dirty read, and if you return the newest, so if you return the stable value, which we'll see in a minute, you can preserve the strong consistency semantics, but if you return the newest available version of the object, this is effectively an eventually consistent read. And they make like a little kind of aside that says, well, if you maintain a session guarantee with a particular node, because of the way the replication strategy works, you can guarantee monotonic reconsistency for a given object, right? And so that naturally holds because we know that those things will only ever get greater as messages are kind of being propagated through the system and acknowledged. But as soon as you break that session guarantee and you talk to a different node, you sacrifice those consistency properties. You sacrifice monotonic reconsistency, and you fall back to eventual consistency. And finally, they present this thing that they don't really talk about enough. They kind of assume a kind of a monotonic counter for versioning, sort of, in the paper. It's kind of implicit in the diagrams. But they talk about the notion of a restricted eventual consistency. That's my name for it, not theirs. But this is similar to things that we've seen in... I can't think of the name of the database that was at UC. It was a UC Berkeley research paper, but you have this idea that you can do maximal bounded inconsistency based on versioning or time, right? So I don't want to read a value that's older than some physical temporal time, which is problematic, but you also can do it based on versioning, right? And so in modern systems and the work that we do at CRDTs, some of this versioning stuff was done with version vectors, but you also can do this with a monotonic counter as well. So how does the algorithm work? You probably already can figure it out from the description I gave just a moment ago. Replicas will store multiple versions for each object, and these versions will, each replica will either be in a dirty or clean status depending on whether it has updates that haven't been committed or updates that have been committed to the system. The acknowledgements that flow back from the tail that are required for error correction when nodes are failing in the middle of a chain, these acknowledgements are used to mark objects clean. So they maintain a version number that say which objects should be kind of marked clean and like kind of moved. And this is how we see the system kind of make progress. And this removes other versions, so versions that were previous clean that no longer need to be read. And finally, read operations can either serve the dirty value, so the unstabilized value that we know that hasn't been marked clean yet because of an in-progress write operation, or they can return the clean value. And we'll see a diagram of how this works, but it requires a second TCP round trip to ensure this. And they make this interesting observation. I love it because if I remember correctly, and I read these papers like 5 months ago, and so I could be kind of short on the details here, but if I remember correctly, they actually say in the paper, this is an interesting observation, which like such a weasel word, right? Because it's like, well, if it's so interesting, let's talk about it, right? Like write a section on it, right? But like the interesting observation, and like no disrespect to the authors, I just think it's funny the way it's proposed. But and I think there's an interesting observation that says that, well, now we can't totally order reads and writes, right? Because any node can service a read. So we only actually can provide a total order over reads on particular nodes based on read and write interleavings per node. And based on the tail, right? Because the tail is an implicit sequencer for the system. So I don't know, it's interesting. So how does this look from the diagram? So I used the one straight from the paper. So we have any of the nodes in the system take read requests, and if all of the nodes are clean, so if we imagine this is the beautifully wonderful QES system that exists at every company in the Bay Area, then we can return the object right off disk, straight back, right out of the cache. But realistically, real systems look like this. So we have write operations that come into the head. We have acknowledgements coming back from the tail. If we read from the tail, we can read a value and return it immediately, and that is a clean read. Otherwise, if we have a value come into the second replica here, where I have values 1 and 2, we either can do a version request, which is a second TCP request, to the tail to get just the version number that is stable and return that to the user, or we can return the dirty value. And this is the difference we get between those consistency models. And the paper posits effectively that the cost of doing this request, so this is the thing that I don't buy in the paper actually, that I don't buy fully in a real system, is that they posit that the version request, because it's a TCP request that only requires a single integer, instead of the full payload of the object, is more efficient. But I feel that is purely based on the workload that they provide, because with smaller objects that might not hold true, and who knows what the cost of doing TCP setup and teardown is for these connections if you have a network that isn't magically reliable, where you can just keep alive that path between those two nodes, right? So under churn, I don't know if these things necessarily hold as one would imagine from this diagram. So, I mean, another interesting thing that they put in the paper is that they want to kind of make a better API, right? So they don't want to have just this kind of key value API. So they do things in 2009 that we just kind of started to see in some of these object stores, right? So they have the ability to say, well, if you're just storing binary objects in the database, you can just append data to those data structures by shipping the delta, which is an interesting thing, right? Who knows how correct that is? Who knows how safe that is, right? But it's an interesting thing. They say, well, if you store like a counter or something, we can increment and decrement at the API level, right? So this is the thing that we see like with CRDT-based systems, like React and things like that, and as well as systems like single machine systems like Redis and the like, right? And then finally, they provide a test and set ability, so you can kind of do a CAS operation, yeah. Yeah, so this is like super weird because it ships it and it's unclear. I remember in the actual paper, so I think or maybe I'm not remembering, but it's unclear if the head attempts to verify that through an asynchronous version request, read it and compare it to the value that you're setting. So you send the version number, and then but I don't know if that's being done at the tail or the head via an asynchronous version request. So that's interesting, but. What's that? Yeah, no. So this would be comparing. This is explicit, like get the version, compare the version number. So this would be similar to something you'd see like in like a Paxos type system, right? Like abstraction you see in a lot of these Paxos systems. Yeah, sorry, that should be more clear. So finally, they provide a multi-key API. So they say, well, you can run multiple chains if you want to do an atomic operation across on a single chain, and the objects are co-located in the single chain. So this actually relies on metadata being in the response about where objects are located. Then you can ship an update that has like multiple changes in it, and it can apply those atomically or not. And that's mainly just an optimization where it ships it together as part of the same payload in the wire, right? And then, yeah, multi-chain, yeah, sure, we can do multi-chain, just two-phase commit, why not? I mean, that's great. So anyway, so in terms of chain placement, this is like kind of the other contribution that they present in this paper is the idea that we may want to do multi-data center chains. And this comes up a little bit in some of the subsequent literature, right? And so with this, they specify 3 placement strategies. And these are basically kind of like, they just very iterative on each other, right? So we have implicit data centers with global chain size, explicit data centers and global chain size, and then explicit data centers with explicit chain size, right? So this is like really trivial. You just get to pick and match like how many nodes you want in a DC, how many DCs you want, right? And then it will establish a chain. And what they say is, well, if you like are okay with dirty reads, like kind of a localized DC level, so you can get kind of you say, well, I want the total load in the DC, or I want to only read this value if all of the DCs have it. You kind of get to pick and choose based on what you want the latency to be, where you make your requests. So that's like really opaque. So kind of what does that look like? It looks like this. We have 3 data centers. We have 3 chains within the data centers. And they make the argument that, well, it's much better to just kind of only ship from a single node between DCs, right? So you don't have like kind of a full mesh between all the DCs. Yeah, okay, yes, we know this, right? So that's kind of the main kind of optimization that they propose. And then they say, well, within the DC, if you want to guarantee that all of the nodes within the DC have a value, then you can locally route to whoever the DC local tail is. And you're like, okay, well, that follows pretty naturally as well, depending on kind of how you want to weaken the consistency guarantees you get for a particular write operation. So one of the things that I think is interesting in this paper is they propose the idea that, well, when we disseminate updates, we can just use TCP multicast, right? So we'll just broadcast this message to all the nodes. And then we'll just send a signaling message, right? And then we can just multicast all the acknowledgments, right? Because, like, I mean, everybody uses multicast on Amazon, right? Like, of course, yeah. I mean, that's a thing. That's pretty awesome, right? So, and again, if you don't know how this might work, I drew this really simplified diagram that shows, I send all these requests, and then I send a sequencing message, right? So again, we're kind of making these arguments that sending version numbers is a lot cheaper than sending full objects, but like a lot of these things are dependent on how the system is really running and kind of what your environment looks like and kind of like how pathological your network partitions are based on, if you really cheap down on your networking hardware or something, like Amazon. So anyway, moving along. So this is a paper that actually, I'm going to talk about a very small part of it, the chain replication part, but this is interesting because this paper is like way out of my field. It's like, I think, way closer to Nathan's kind of work, which is based on like optimizing and lower latency processing, like kind of OS level kind of work, right? So this is kind of out of my area. And so we're going to talk about this system called the fast array of wimpy nodes. And this is composed of 2 kind of major components here, a system called fawn KV, which is key value store, and fawn DS, which is a data store. And so the fawn KB is kind of like a routing abstraction on top of a bunch of fawn DS instances, okay? And so what the fast array of wimpy nodes research kind of presents is this model for low-power data-intensive computing. So they want to have kind of these massively powerful clusters. They actually want to compete with like modern clusters. They compare themselves to systems like Dynamo and Cord and things like this. But they want to do it with low-power CPUs and like kind of flash storage. And this is what they present as the fawn architecture. And what they're trying to do is kind of close this I/O CPU gap. So they present a lot of research in the paper, a lot of which I don't understand, that basically says that for low power, like for systems where you're mostly I/O bound, it's more efficient to have lower power CPU that use lower power because you spend too much energy, basically, with CPUs that are clocked too high when they're idling in like an I/O wait space. So this is kind of what this paper kind of posits and presents an architecture for. So again, this pairing of low power embedded CPUs with flash memory, and they want to satisfy the same latency and same capacity as the existing kind of state-of-the-art systems that have been published at places like SIGMOD and SOSP, right? So it's a multi-node system named Fawn KV. This is going to look really familiar to you based on a ton of other systems you've seen. It's horizontal partitioning, or sharding, as we call it, across a bunch of log data structures, right? And so, wow, that sounds like it's REAC or Cord or Voldemort or Cassandra or any of these things, right? So it sounds very similar to these things. And oh my God, there's a ring, right? So I don't even work at Basho anymore, but I still get to show the ring, so that's badass. So how does this work? So we have a ring, and this represents a hash space. We tokenize the hash space, and clients claim positions on this hash space. And what we do is we kind of take contiguous partitions to establish chains. And so here are our chains: A1, B1, C1. B1 is the middle position for the chain starting with A1. It's the head position for the chain starting B1. And we see how this kind of naturally falls out, right? So this is pretty straightforward. This is like pretty kind of textbook kind of consistent hashing combined with hash space partitioning that we see in a lot of scalable systems today. So it shouldn't be really anything new. And again, these kind of same chain things apply. So the way Fawn KV works is, it's basically a log structured, like a log that you write to. It maintains pointers to the positions in the logs by key. This is very similar to like lots of data stores that you've probably seen already. When we write a new value for a key, we append it to the log, we update the position of the mapping from the keys to the positions in the log, and then we have an asynchronous compaction mechanism that kind of removes the dead references, right? So this is pretty kind of textbook data structures for databases, right, to make them optimized. And then they do aggressive caching, so they separate kind of back-end nodes which do data processing from front-end nodes which are proxies for serving data. And they just try to aggressively cache values based on log positions, all of this stuff, just as much as possible to reduce the latencies. And so in terms of the ring, we have to deal with the fact that the ring is going to churn. Nodes are going to leave and come and all of this stuff. So the ring is going to kind of change. And so what we need to do is that when a node leaves a particular portion of that ring, we need to kind of do this two-phase process, which is we pre-copy the data for the leaving node or the joining node, and we ship it. And then once we do the pre-copy to get the bulk over, before we activate that node as being active in the ring, we just do a final flush to be all of the data that we've accumulated as writes during the during the period where we've done the pre-copy. And again, it's a pretty standard data structure technique that you've probably seen all over the place, right? So there's not anything like really interesting about that. So let's talk about the failure model. So again, fail stop. Nodes are assumed to be fail stop. Failures are detected by front ends and back ends timeouts. So front end nodes ping back ends ping front ends, and we use just regular kind of timeouts to detect the failures. Sorry. Yeah, I mean this is naive, right? But the best part is they acknowledge it. They actually say that like the backend nodes don't ping each other, and they may never know that one of them's no longer there. And the front end nodes ping the backend nodes, but the front end nodes don't ping themselves either. So yeah, they're like under network partitions, we probably are going to have a problem. But they acknowledge it, and they say this is a section for future work. So to academia. So, moving right along, we'll get to my favorite. There's a real favorite of mine again. Scott Fritchie is a coworker of mine. This paper made the rounds a bit. What was it, like 2 years ago? I think Kelly Summers tweeted about this paper. She like found it because High Scalability, I think, tweeted it or something, and they were like, "Oh my God, there's this crazy paper on chain replication." And I love this paper because Scott worked really hard on this system, and Scott kind of walks around like he's got like the scars from working on this system, and it's nice, right? It's got that nice Erlang burn going to it. But so we're going to present a system called Habari. Habari is an open source system written in Erlang. It was written when Scott was in Japan at Gemini Mobile Technologies. And they were a company that made a chain replication solution that was a bundled product, like you kind of like, I think they sold it at the time, but you would get this and you run it on site, right? So this is not like a SaaS kind of thing or platform as a service, whatever we call these things today. And this is kind of an experience report that Scott wrote about just kind of the trials of tribulations of actually running some of this stuff in production. So I think it's a really great read. Yeah, it's fantastic. So anyway, the Habari system has two abstractions that it presents: physical and logical bricks. So physical bricks are either virtualized machines or physical machines, and then logical bricks are kind of the chain, the serialization kind of points that we use for each of the chain instances that we stripe across these physical bricks, right? And this is for fault tolerance. One of the lesser notable things that they briefly only talk about is that Scott wanted to provide a SQL-like table abstraction over chain replication. So you have like a table that represents the data in the database, and you have timestamps and stuff. But you don't really get kind of what you'd really want from this. So I feel this is kind of a poor abstraction that's presented. Similar to FonKV, we have the notion of consistent hashing, multiple chains. We're going to partition them across a hash space. It's going to be very familiar. You're going to see a lot of these techniques repeated over and over by researchers. And they disseminate information through clients. So clients cache a lot of information about where to go to contact nodes, where chains are, and things like this. And this improves efficiency in practice. So this is kind of what it looks like. So here we see the physical bricks that are running vertically, and we see the logical bricks kind of running horizontally in chains. And so we see that he does this kind of striping in this mechanism to kind of just get these scattered across the physical bricks to kind of just improve fault tolerance and have better distribution of load for the chains. And obviously this assumes kind of a uniform distribution over the data load. The workload. So we're not going to kind of talk about we're not going to talk a lot about how the system works. We're going to talk about like all the hacks Scott talks about in the paper. So the first hack that Scott talks about is, I actually have to go back. So in this diagram, each of these things here, the head 0, tail 0, these are what's called the generic server abstraction in Erlang. And so what this is it's a tail recursive looping process that reads messages out of a mailbox that's written to asynchronously by nodes in the network through message passing, and it processes these messages. So the observation that they make while running this is that, well, it's really damn expensive to open a file if it's not open yet. So what they do, and they actually found that this was more efficient, was that they would spawn a process, and they would do this asynchronously for a request coming in that would read the data to fill the page cache. And then, yeah, they read the data twice, because the second read out of the page cache would allow them to block the gen server for slightly less time than it would take to block it if you actually had to call the file open file call in Erlang. So that's a pretty crazy thing. And I don't know if this holds true over Erlang now, because this is 2010. The Erlang VM has had a lot of problem with native function calls and NIFs, like NIFs or what we call them. And so a lot of this stuff has been better, and it's mainly problems with scheduling that cause a lot of this. So this, I think, is a really crazy, awesome takeaway from the paper. And who knows how this would ever work for systems that aren't Erlang, right? A second one is rate controlling. So Erlang, if Erlang unbounded message queues, man, I feel like Cliff Moon should be here, like just so he could like walk on stage and like say something when I say unbounded message queues. Erlang's got unbounded message queues. The mailbox can grow as big as your memory is on your machine, and messages can sit there for very long. So they had to basically add a process that would silently drop messages, basically to shed load when the Erlang VM got backed up and there was too much synchronization on the mailbox and things like this. And this is just what they had to do in practice to make the system work. Finally, with that ring I showed before, under ring transitions, there were race conditions where you would route between nodes that had different views of the ring. And because of that, you had monotonic hop counters had to be introduced to ensure that you didn't have routing loops that would go infinitely and blow up the mailbox. So again, unbounded mailboxes and transitions in distributed systems, these are really hard things to work with. So this is another idea of having rate control, just so the system could have predictable latency. The configuration agent is talked about as just being a single machine. Again, centralized configuration management. And they present a solution kind of for saying that you can do quorum intersection style operations on the replicated state and store it in the logical bricks themselves if you want higher availability. But they acknowledge that the single configuration agent's a problem. So yes, back to my favorite topic, fail stop. Yes. Okay. So Scott calls this the Erlang anecdote from Erlang questions. I don't know who originally said this, but I'd love to find. I mean, I'm probably friends with them, right? I mean, there's only about like 100 Erlang programmers in the world. So whoever said send and pray, if you watch this talk, come talk to me. So Erlang message passing can drop messages for sure. A lot of people don't believe this, but this is a real thing. There's an entire academic paper on Erlang specifically. The only guarantee that Erlang makes is prefix delivery. It guarantees ordering. But it says that, well, if the connection drops for a second and you sent 50 messages, I could deliver 1 in 50, and that's fine. Like from the programming language semantics, that's fine. And there's an interesting entire talk where there's a good 5 minutes, I think, if I remember correctly, dedicated to this when Simon Marlowe, when working on Cloud Haskell, was implementing the unified semantics for Erlang, which is another paper that was published, talks specifically about this problem because this is a very difficult problem to do. So yes, messages can be dropped all the time, all day. That's crazy. And so what did Scott do? Well, Scott came up with this idea that you could make this application called the partition detector. And what this would do is it would send heartbeats on 2 physical networks. So they deployed 2 physical networks in the customer data center, and they would heartbeat on both to try to detect partitions. And they still had problems. Oh my God, who would have imagined, right? But I mean, come on, give him credit for the ingenuity, right? I mean, shout out to Scott Fritchie. And it's still problematic. Why? Because sometimes it's not even the network, right? Sometimes it's like the runtime system. So netkernel has tons of problems with mutexes and things like this where the VM can appear to just disappear for a few minutes because it's like off in La La Land doing something. Who knows, right? They found a bug, and the paper talks for about 4 or 5 paragraphs, I think, about a specific bug in the netkernel where some race condition between 2 processes causes this. Distribution port buffer. So the Erlang is a full mesh between all nodes. And if I have an Erlang's claim to fame, right, I can run 200,000 processes on a single machine, single VM. I could run 10 VMs on that machine. Well, the thing that they don't tell you is that it all goes through one TCP connection. And that one TCP connection has a 128K byte buffer. So that's a problem, and obviously we ran into this quite a bit with React. Because people like to put objects in React that are not small. And then finally, the VM has been notoriously problematic with scheduling because of NIFs, because the VM was designed to be a reduction counting VM. And for a while, native calls were considered a single reduction. So if you ran a native call that, I don't know, ran sleep for 60 seconds, and it counted as 1 reduction, and you have a reduction counter that preempts processes at 2,000 reductions, that isn't really compatible. So this has been an area of significant work on the Erlang VM. So anyway, so when failstop disappears, when failstop is violated, even when you have 2 physical networks that you run an application on to detect this, even when it's violated, you run into some really bad problems. And so the first one is that you can churn your chains so fast that you end up with chains with no nodes. Because you remove a node falsely because it was incorrect, you add it to the back, you add it to the back, but you can't activate it till you synchronize the state. And then when you do synchronize the state, you've lost the other node that you were synchronizing from because it's been falsely detected. So they ran into situations where on-prem at customer sites, they would have chains with 0 length, no progress, the system just wouldn't work at all. So that's a problem. So moving along, I think we got 3 papers left, and these are fast ones, so I won't keep you anymore. I know everybody's probably thirsty or something. I don't know. We'll talk about hypertext. So hypertext is a really difficult paper for me. Not for that reason, for those laughing. But Hyperdeck is a really difficult paper for me because there's a lot of really heavy math that I don't understand because I'm mainly working in a kind of a completely different kind of PL area. This is not an area I'm interested in. It is an area I'm interested in. It's an area I don't have time to focus in, really, right? So Hyperdeck is from Goon, who's the author of that tweet earlier. This is the systems group at Cornell University who's famous for so many great things, and these guys are doing a lot of Bitcoin research now if you're into that. So Hyperdeck is basically kind of makes this argument, and they specifically kind of jab Dynamo, Cassandra, and React pretty aggressively. If you remember the blog post from when this Hyperdeck stuff was coming out, they basically said eventual consistency was like the worst thing ever, and it was terrible, and it was like, I forget the name of the post, but it was really aggressive. And so they said, well, the only mechanism you have, you give away all of this stuff, the only mechanism you end up with is primary key access over objects in your system, right? And so they say, a lot of the approaches that have been previously taken, and at Basho we ran into this quite a bit, how do you do indexing partitioning for objects in a database? It's a really hard problem to get right and efficient. How can we provide efficient secondary indexes in search? So search over attributes for an object. So we want to tag, if we're writing an object, we want to tag it with some attributes. So if I write the Chris key, I might say university, UCL in Belgium, and I might say, how many glasses of wine does he drink concurrently? And I'd say 2, because I have 2 here. So these would be attributes that we'd say. So Hyperdeck makes 2 contributions. The first one is this idea of hyperspace hashing, which is that we're going to use all of the objects to basically hash the right into some place in this multi-dimensional Euclidean space that I have a diagram of. And then the second one is, and this is the one that we care about for this talk, is this idea of value-dependent chaining. So this is a fault-tolerant replication protocol for writing primary objects and secondary attributes that ensures linearizability. So this is what the diagram looks like. What we do is we take this multi-dimensional Euclidean space and we partition it so each of these cubes represents a node in the distributed system. When we want to search for John Smith, we look for the intersection of the hyperplanes, basically in this space, and that tells us the nodes we have to search. So we say that this right here are these 2 nodes in the system. Maybe there's 8 nodes there. These are where we actually have to search. So the way this works is that when writes come into the system, we use the primary key to designate what we call a point leader. So this would basically be, if we go back to that idea of having all those different chains in that ring, this is how we select out of that ring, right? So this is specific to their use case with this multidimensional Euclidean space, but the notion is the same. This is how we select the head of the chain, right? And we don't have these chains established a priori. What we do is that to determine the next item in the chain, we hash the attributes. So we're going to sort these attributes maybe in a particular way, and then we hash these attributes to find what the chain for that write actually is. So in this example, I've highlighted the sections I want to talk about because we're going to come back to this a few times. And this is not the greatest diagram to use, but for anybody who's interested in reading the paper, I wanted to use the one in the paper as a reference because I thought it'd be helpful. So in this case, if we're writing this object and we have these attributes, John and Smith, this write is going to write the primary key. It's going to hash the attribute John and then hash the attribute Smith, right? Let's say. So we're going to determine the next node. So we know to go to H2 because of the secondary attribute, and we know to go to H3 for the third attribute. So now the challenge to make this work efficiently is that if we have to relocate values, such as when an secondary attribute changes, we need to compute what the old location would be to know where to eliminate the data from, and then compute the new location where it should be written. And the way we purge the state, actually, from the old positions is that we're going to do this through acknowledgements. So to walk through the example again, with update 2, we perform the write on H1. We go to H2, which was the previous attribute from the previous write. We then go to H5, which is the new attribute for the next write, for that same attribute. And then we move to H3. So this shows how we take this process where we go to the old location where the old data was to set up the mechanism to purge, and then we go to the new location to perform the write. As the acknowledgements flow back through the chain, again, the same kind of acknowledgement thing we've been talking about this whole time, this is when we clean up the data in H2. So the problem that you'll see here is that an update 3 might happen like right after, right? And this update 3 might be doing something with similar attributes, let's say. And that might kind of race to H5 with the other one, right, and get there first. So the idea is that we need to include sequencing information from the head node to know what updates should be arbited in what order, right? So this is just to eliminate the fact that we might have to visit more nodes on the secondary write. And so to address the issue of fault tolerance, because in this diagram we have here, if I go back, there's no notion of fault tolerance here because every position in this graph is where I'm storing a single attribute. What I have to do is say, well, H1 is going to form a chain itself, and H2 is going to form a chain itself. So this is kind of this multi-dimensional set of chains where each node in this graph represents a chain itself, right? And this is how we get the fault tolerance property that we want. So it's the application of chains to solving a different problem, but then also using chains to solve the fault tolerance problem. So I think that's a nice kind of, there's a nice property of composition there that I like. So, yeah, so this is done just through the traditional mapping that you saw in that diagram. So, moving forward, this system provides per-key linearizability for operations. We don't acknowledge writes until we've processed all of the attribute writes and everything, so we block to acknowledge the user, same as we saw in the first paper of the talk. And finally, we get this nice property that so many other systems, such as React and Cassandra, I think at least has some notion of problems with this. I don't know if that's changed recently because I don't work on databases anymore, thank God. And so search results are guaranteed to be the results of the currently written object, right? So we don't have a asynchronously flushed index that can become out of date because we don't have a transactional mechanism to write these objects. So this is a nice property to have. Or this is the property everybody wants. Yo, but what about failures, right? So I tweeted to Goon. Well, I didn't tweet to him. He just responded to me that what about failures, yo? And so I did a lot of searching on the internet on this site called twitter.com, and I found that yes, we use the fee accrual failure detector. So this is a failure detector that's pretty popular. We've seen it in a bunch of systems. I'm pretty sure this is the failure detector that Akka is currently using. And I love this little comment here. Fancy name for estimating round trip time and cleaving a node when it's being slow. It's just that's just a paper. And it's just, I don't know. It's so dismissive in this elite hacker way. So I don't know. I have to get good trolls into him because he trolls me hard too. So anyway, the paper actually has almost nothing about how failures are handled. There's some stuff on the blog, but on their docs and their blog. So I'm assuming that the failure stuff maybe wasn't super novel, so they didn't talk about it. But it'd be nice if it was easier to find, because this tweet took 10 minutes to find or something, and I'm just I should just be able to Google failure detector hyperdex or get a page on it or something, right? Because if I want to put this in production, that's what I want. So moving along, I think we have 2 papers left. We'll briefly talk about this system from some colleagues of mine in Portugal called chain reaction. And this is a causal plus consistent data store based on chain replication. So the motivation of chain reaction is that per-key linearizability is too strong of a guarantee, requires too much synchronization within a single data center, right? So within multiple data centers. So we kind of all agree with that, right? Unless we have Spanner, but I don't have Spanner, so I have to use a system like this. And what we provide, what's provided in the system is causal plus consistency. So does everybody here familiar with causal consistency, which is a weaker consistency? No? No, okay. So causal consistency, I'll give you the poor man's 1 minute definition, is going to say that if I see some objects in the system, so I read some objects, and then I make some change based on those objects, when I write my object back, I encode kind of the dependencies of what I saw. So if I see the change I just made, I will always see all of the causally dependent causally related things that caused me to make that change, right? And so the classic example of this in the literature, which is a funny kind of literature example, so I believe this is originally from the COPS paper by Wyatt Lloyd, is an example where I'm on Facebook and I'm friends with my professor, and I'm going to post some really nasty spring break photos. So I unfriend him, and then I add the spring break photos, right? And the classic example says that in an eventually consistent system, I can deliver the spring break photos to the other replica before the permission restriction, and the one is dependent on the other. And as a user of a system, as a kind of a person, you would want to reason that yes, I don't want those pictures to be seen. That's why I did that in this order, right? So causal consistency is kind of a consistency model that's not as strong as totally ordering, but not as weak as eventually consistent. And it provides these very useful guarantees that you'd want in the system. And so the distinction we make here as causal plus is that causal plus says that any concurrent operations can always be merged. And it's a very anomalous merge, and we'll talk about that in the next slide. And so what they also have to say is causal consistency traditionally, if you've read like the Peter Bayless 2 papers on this and any of the literature that predates this, is extremely expensive because you have to explicitly encode all of the dependencies in every write, and this kind of just grows unbounded, right? Because most of the writes that you do on a serialized machine are related to each other for some reason. And then finally, we just talk about how to optimally distribute this in a geo-replicated setting. So what do I say when I mean conflict resolution? Well, causal plus consistency, well, it was originally formalized as last writer wins. Well, sure, if you have synchronized clocks, last writer wins is definitely convergent. That is convergent. You don't guarantee you'll get anything that means anything, but everybody will get the same thing. So, I mean, at least it's fair. And, in more recent systems, so one of the systems I work on called Antidote, which is a CRDT-based system, shows that, like, in practice, we have data types that allow us to have these kind of mergeable data structures that have meaning and are not, like, as vacuous as a last writer wins guarantee that we see in some databases today. So what is the observation they make in this paper? So the observation here that's really interesting is that this update propagation invariant that we said, where all of the nodes kind of have lesser state, well, that's interesting, right? Because that says if I read objects on the same chain and then I write them back, the node that I write to, all of the nodes before that will have the same information. So it says, well, I can't read from any node, but the node that I do write and get acknowledgement from, I guarantee that any node earlier in the chain will be causally consistent with a previous read that I made at a later node in the chain. And so this is a really interesting observation that they make. And they specify K to be the number of nodes in a machine where you have to kind of have this acknowledgement for to get this guarantee that all of these previous nodes have this causally consistent guarantee. And to kind of encode causality, they encode a notion of causality that's explicit. So they explicitly encode all of the objects that you had read for that write. And then when you go to write them, if we know that some object is stable across all the nodes, when the write comes in, we can just scrub it out of the metadata. We don't need it. And this is how we keep the metadata reduction low, is by performing this scrubbing process to say, you said that you depend on value A at time 1. A at time 1 has been stable for like 20 minutes, so we can just scrub this out of the metadata. And then when you extend this to multi-data center, not to like dig too deep into this, but when you extend this in multi-data center, this is, it follows naturally that we can just model this with a version vector and kind of do this same process with a version vector. And then we use this version vector that we gossip around, so we keep pairs of what we've seen and what the remote nodes have seen, so our views of what the remote nodes have seen, and then we can perform this purging based on these vectors. So this is a technique that's seen in many databases today, is not really specific to many research databases today, which is not really specific to chain reaction itself. And so just to give you an example again, we here say that given that update propagation invariant that shows that nodes that appear earlier in the chain will always have the same data that the previous nodes had. And that allows us to say that we can kind of make subsequent requests to earlier nodes, like under failures or to do better load balancing, and still have this guarantee. And this requires the clients being smart to know which nodes to contact to. It requires session guarantees. And if you ever want to communicate cross-object, you have to guarantee that you use a vector. So the vector needs to be used cross-DC and cross-chain, right? And so the design of that system is mostly similar to Fawn KV. So it's getting long, so this is the last paper. It's gonna be fast, I promise. And so bringing it back to another Robert Van Renesse joint here. This is the final paper, which I think is great, which is called Leveraging Sharding in the Design of Scalable Replication Protocols. And what we're gonna see is things that are similar to chain reaction. We're gonna see things that are similar to Fawn KV. We're gonna kind of see a lot of reoccurring themes in this work with some notable exceptions. So, the algorithm presented in this paper is referred to as elastic replication. And this paper makes, I forget if it's two or three, I think it's 3, contributions. So the first one is the notion of customizable consistency. Is similar going back to the crack paper. We say if the user will opt in for weaker guarantees on values that it wants to read out of the database, we can reduce the latency by contacting any node, right? So this is kind of a thing that we've seen. We kind of intuit it just by looking at the diagrams and the systems. here. And so this is kind of straightforward from everything we've seen. It might not be straightforward if you only read this paper first. They introduce what they refer to as a notion of robust consistency. So this is the kind of the big reveal, right? They introduce a protocol that does not require accurate fail detection, which is kind of nice. And finally, they want to eliminate the need for a central reconfiguration service. So this is like, really the grand finale. Like, it's getting serious here. So again, kind of going back to fail stop, and talking about two challenges specifically, the two challenges that we talked about at the beginning here were that primary backup, false suspicion allows you to promote a node, a backup node, to be a primary when it shouldn't be, right? And so this can be problematic if not all of the clients kind of know this, and you can kind of have concurrent writes to a primary that actually the old primary, while it's still online, after you've promoted the backup one, if some message is delayed or you're racing, that allows you to write some value that may never ever be read again. And finally, with quorum intersection, as we've seen with some of these systems that use ring-based reconfiguration, under reconfiguration, quorums might not intersect. And in terms of React, we actually say in many cases the quorums won't intersect, right? Like you have no guarantees. People always want reader and writes, and in React, if you want it to run in the available mode, we actually don't guarantee that whatsoever. And that was a very contentious point back in the React 1.0 days, right? And maybe the 0.14.2 days as well. So how does the algorithm work? So in terms of, if you think about the algorithm, we're going to have a bunch of replicas, and we're going to imagine that the state each replica stores, so each of those nodes in the chain is going to track a history of objects that have been written, so commands, let's say. So it would track, rather than keeping objects, let's just say it keeps a log of like changes to those objects, right? Just to make this easier to reason about, right? So these are write operations that are stored in some append-only log. And so at any one time in the system, we know that there's going to be some prefix of that log that has been stabilized across all the nodes. And this is the notion of the clean versus dirty, right? So if we have a log that's at position 10, and then we have some stable position of that log that's 5, 5 is the position of the log that we know where those writes have been stabilized. We know all the nodes in the system have those writes. And so what we do is we asynchronously can kind of promote the greatest common prefix as stable across all of those nodes. So as we write to these nodes, they report back their position in the log. And once we know, so at one case, some of them will be at different positions, we always can compute this greatest lower prefix, and we know that is the value that has been stabilized. That is the log position that's been stabilized. And then we can promote that as kind of stable. So to give an example with a diagram of how this works, we say that we're going to perform some write operation to node 1. We call this command called adopt history, which basically is 1 communicating to 2, to 3, to 4, which is saying this is what my log has. Take some portion of my log, like adopt my portion of the history into your log. That gets adopted. These messages going back here are acknowledgements, so the same acknowledgements we had since the beginning, but now what they include is the history prefix. So each of these nodes will say, I'm at position whatever in my history. And so finally, when that response goes back to the user, back to the leader invokes a command called an atomic transition called learn persistence. And what this does is it takes the greatest common prefix across all of those values, and it promotes that from the history to stable. And then stable values are what you allow to be read from the system. I keep hitting this thing and it's not working. So again, now to ensure safety of this algorithm, we need to ensure that if any node suspects any other node, even incorrectly, of a failure, that node needs to go into a state which is called wedge, which means that that node stops accepting any requests for the current configuration, and we model these configurations as epochs. It stops taking any requests, and the only operation it can perform is make things stable that it knows all other nodes have. And this is how we preserve safety, to prevent values from being written to the log that should not be written. But you can have a system that's safe without being live, so we also have to ensure liveness. So to ensure liveness, replicas need to be reconfigured when they notice that another node in the system has been wedged. So when a node in the system has been wedged, we issue a reconfiguration. This advances the epoch, and some configuration service does this. And what this does is when it's reconfigured, we preserve the UPI, the update propagation invariant, under reconfiguration, and we just disseminate the state forward using the inherit history command. And so again, I don't know why I have this diagram twice. It shouldn't be there. I added it on the way over here on the Caltrain, so that was a mistake. So that makes an algorithm that can handle these failures that are not accurately detected because nodes shut down. We reconfigure things. We ensure that some configuration service reconfigures them to be the available nodes. Then the system propagates its thing, promotes the history, and makes progress. So the other kind of thing that they do is talk more about this idea of horizontal partitioning. So we want to run multiple of these chains and shard across them. And the observation that they make is like, sure, this has been done before. It's been done in all these other systems, in Crack and Fawn KV and chain reaction. But the contribution that they provide is that they say, well, if we have all of these rings of chains and each position on the ring is a chain, then what we can do is have the chains reconfigure each other, right? So we say, as long as the previous chain has some valid member in it, it can configure the next chain, and we can do this in a ring and have the system self-configure. So, I mean, obviously the problem with this really, novel observation is that you still have to understand how you choose the ring, right? So, like, even if you want to have a ring that's maintained by 10 chains and all of the 10 chains maintain each other, you still have to have a mechanism to establish that there are 10 chains and what the members of those chains are, right? So, again, we get back to this problem that we still need this external configuration service, right? We kind of skirted around some of the fault tolerance problems, but we still need to ultimately have some notion of distributed consensus to solve one notion of the problem, right? And so I think that's an interesting observation that you can make from this work. And so this is kind of what that looks like, is that we have these chains here, and they configure each other, and we can have failures within them. But again, we still need to have the configuration service establish how many of these groups there actually are. The final caveat of the paper is that now that we've done this and these nodes wedge each other and get reconfigured and we have epoch-based reconfiguration, we have to serialize all the reads at the ingestion point now. And the reason we have to do that is we have to ensure that all of the members in the chain have the same view of the epoch. Because some of them might be wedged. And if we send it directly to the tail may be partitioned from the configuration service, and the configuration service may have advanced the epoch, and the tail may have not noticed a problem yet. So again, we're kind of back to this problem. And so the authors say, well, we can solve this with leases, and I'm highly skeptical of that solution, obviously. So, and finally, reads can be serviced by other nodes because we can read out of the history, so the non-stabilized values, if we're willing to sacrifice eventual consistency for a weaker form, such as sequential consistency. So, to wrap up, it's been really long. I apologize. Hopefully you enjoyed it. In summary, I gave you this whirlwind tour of chain replication. I hopefully gave you kind of, I don't even know how many years it was. I guess, almost 7 years at this point of research. Fail stop is really hard. We know this is hard. It's hard to get right. A lot of these algorithms assume it. Fail stop is a really nice way to write papers and reason about systems, but it's not always practical, especially if you're working on very large networks where failures are basically inevitable at a high rate, right? Distributed consensus is still ultimately required, right? Like, this is the idea of who watches the watchman, right? Like, eventually, as much as we want to make systems self-configure, eventually we have to kind of establish that there's some notion of initial configuration, like a priori configuration that's needed. Otherwise, we need some solution for distributed consensus to do this initial configuration of the system. And finally, chain replication is a really interesting technique. We've seen this used in practice with hyperdex. We've seen it used in practice with the Habari system by Scott Fritchie. And finally, Basho Technologies, my former employer, Scott Fritchie is working on a system called Machi, which is kind of a mashup of chain replication and Corfu and Tango from Microsoft Research Silicon Valley, which is super interesting, which I don't know a ton about. I know a little bit about it, but not a ton. And so this stuff is really cool, and you should check it out if you're really interested in the topic. So, thank you very much. I appreciate it. How long was that?
I don't know, but it was good. So if anybody has any questions, we can go through a few quick rounds, and then we can take it to the bar. Questions? Oh, wait. Macaroons for the macaroon god. Yes.
Thank
Questions?
Oh my God, everybody's like brain
Oh.
dead.
No, they're like,
What's up, Brian Fink?
So there's got to be an obvious practical limit to the length of the chain. Do any of these papers go into that?
I think Scott's does, if I remember correctly. Like, I've thought about that problem a lot, but like, I mean, I read these about a month ago. I read most of them over the course of 2 weeks, about a month ago, and I don't remember. But there's obviously a trade-off between fault tolerance and performance, right? And unfortunately, I don't remember the specifics, but I'm pretty sure that is addressed by Scott in his paper, because in his diagram he shows chains of length 2, right? Yes. Right, he shows chains of length tooth, yeah. And like the obvious benefit there is that you would say, well, if you have chains of length tooth, isn't this basically just primary backup, right? But part of it is the notion of there is a performance improvement you get from pipelining, from having the chains, that you don't get with primary backup. If you have like traditional primary backup where you synchronize with the backup to perform the write and wait for the write to complete. Where the chain replication, you get the pipelining. And so David Greenberg, I think, when I was searching for all these tweets, I think that David Greenberg at 2 Sigma had a tweet that said, basically that in practice, what he had observed when he had implemented it was that he did chains of length 2. It was basically primary backup, but he got a huge benefit from the pipelining. Oh, man.
Yeah. I'm not a distributed systems person. I'm a systems level concurrency person. And the more I learn about distributed systems, the more parallels I see with the work that people are doing on systems level concurrency, specifically things like mentioning epoch-based counting for your chain versus epoch reclamation and liveness guarantees. Are you aware of any research overlap where people who are working on distributed systems are collaborating with systems research people? Where there would be sort of more parallels drawn?
That's a really good question. I don't know if I'm the best person to answer that. I think I would talk to her. She sounds like she knows more than I do. But yeah, no. Unfortunately, I can't think of anything off the top of my head. But
so the only one I know about is Midori. It comes from Microsoft.
yes.
Oh, okay. Midori comes from Microsoft Research. It's their attempt at building another operating system just from the ground up. But the interesting thing is it makes no distinction between cores and different nodes. So it's kind of bridging the space of like distributed systems and like cores, or treating different nodes and cores as the same thing.
Cool.
all right, 2 more questions, and then, 3 more questions.
You mentioned one hybrid approach that your colleague is or your former colleague was working on. Do you know of any others? I mean, it seems like some of these things, I looked at them and I thought, that might be interesting if you like mixed in this and this and this and this.
Like people working on chain replication?
Yeah, like with other, like mixing it in with other stuff to make it more viable in the real world.
That's an excellent question. I only know Scott's mainly because I've been involved in reviewing a preprint of a paper on it. So that's primarily where I know most of it from. And I actually never knew the elastic replication paper until I found it in Scott's as a citation. So I don't really offhand, other than like the hyperdex work, which I think is interesting because it's applying the technique to indexing and fault tolerance, and Scott's work, which is like trying to do like data structure, like immutable data structures on top of it. Yeah, I don't know. Kelly Summers, like at one point, was tweeting about doing some stuff like that. So maybe she's taken that further, but I don't really know of anyone else personally.
So one of the things that you talked about in the crack paper is the overhead of TCP. I was wondering if any of these CR protocols have been reviewed with RDMA, like the work that was done by CMU with Herd.
That I don't know. I don't know at this point. Yeah, sorry. I'm just failing every question here. It's like thank God this is not my defense, right? Like, Jesus Christ. It's true. Yeah.
So maybe this gets at like why people like me are being weaselly and favoriting tweets, but
we're being unfavorited to you. We're unfavoriting you. No. Oh, yeah.
When is chain replication a good idea?
Man, that's a really good question. Yeah, I mean, I don't. That's a really good question. I mean, the argument is that it's so much more high throughput, and you don't have to have the additional nodes, right? But so like when I looked at when I came across the elastic replication work, I was like, holy shit, this is great. Because the original paper, I was just like staring at it, and I'm like, this does not make any sense, right? Like I worked at Basho, and like all we thought about was partitions. Like literally, we thought about we're like, let's run the system with the partition, right? Like that was like the mode we operated in, right? And so when I saw the elastic replication paper, I was like, yeah, this sounds really good. This sounds really nice. And then you get to that part where it's like kind of like, well, you have to sequence all the operations on the head, like because you have to go through all the nodes to verify that they like kind of agree on this epoch, and you have to have the clients know what the epochs are. And you're kind of like, well, that sounds terrible. And they're like, you know how it is, right? One line, like this can be solved in practice with leases. And you're like, yeah, well, if it could, why isn't it in the paper, right? So there's an interesting question. Is like, what is it really good for, right? And like, have we seen a system run at extreme scale with it yet? And I don't have the answer to that. I don't know. I'd love somebody in the audience to know an example.
Hodges, do you know what?
So I mean, I don't have an answer for your question, but I think your question is extremely interesting. So.
Yeah. So why academics like this is the last question. So, well, I would like to thank everybody that came like consistently through the year. There's a little bit more food. There's the little, like the #1 tiny dessert of America, cupcakes. So if you want a little bit more, there's more wine. And then the bar that we're going to go after is called Bar Basic. So yeah. So thank you so much to everybody. Thank you, Chris, and thank you, Nathan, for killing it.